About 150 yards from the launch pad in the concrete blockhouse are the men and equipment whose job it is to launch the Atlas and monitor its performance. Each technician begins to carry out his part of the carefully rehearsed countdown. Each man is responsible for carefully monitoring a particular part of a missile. Nothing goes unnoticed. And the entire procedure is under the eyes of experts alert to detect and analyze any area of difficulty and to correct it. This flight test, the first launch of an Atlas missile, took place at Cape Canaveral on 11 June 1957. The missile rose in a stable manner, and the booster engine propulsion system operated normally during the initial part of flight. The autopilot guidance system maintained exact control, performing satisfactorily and according to plan. After 25 seconds of flight, thrust in one of the engines began to fail. The control system tried to maintain stability but could not handle the unbalanced thrust. About 3 seconds later, the first booster engine shut down, and a fire broke out in the rear section of the missile. At this point, the missile veered. It tried to recover, then fell back. After being airborne for approximately 50 seconds, the missile was deliberately destroyed by the range safety officer. Although the test might on the surface seem to be a failure, its ultimate results were extremely beneficial. Invaluable data were obtained as a result of the flight test. This information was checked and verified on captive test missiles, leading to changes in designs which were incorporated in later successful Atlas
But NASA is up to the challenge. Modifications and improvements are made, and the Atlas is ready. But as the rockets get bigger and the missions longer, the sheer volume of data involved grows dramatically. The computers monitoring the various functions and system status or the telemetry of this mission are now tracking 2,000 items per second. A confident John Glenn arrives at Cape Canaveral Complex 14 and prepares to board the Friendship 7. Based on their experiences with the two previous suborbital missions, the ground crew has the routine down cold.
Okay, John. You're ready.
A series of 18 flight control stations are chained together around the globe to track Glenn's Mercury capsule named Friendship 7 on its 3 orbits.
Motions out. Color display. Okay, that's fine.
All right, there. Get that meter stood.
All right. Clock's taking. Have a braking high level light. You are go. Order systems, go. Range operations. Mercury capsule, go. All pre-start panel lights are correct. The ready light is on. Eject Mercury umbilical. Oil evacuate. Mercury umbilical clear. Mercury evacuate. Lights on. All recorders to fast. T-minus 18 seconds and counting engine start. May the Weeward be with you, Thomas. Good Lord, ride all the way. Godspeed, John Glenn. 10, 9, 8, 7, 6, 5, 4, 3. Backup clock is started. Fuel 102, 101, oxygen 78, 100, amp 27. Roger, loud and clear, flight path is good, 69.
At last, the United States has a man in orbit.
And I feel fine. Capsule is turning around. Oh, that view is tremendous.
Of Congress. Building on the success of John Glenn's flight, the next mission, to be flown by Navy Lieutenant Commander Scott Carpenter, has been loaded up with scientific experiments. Carpenter will make celestial and solar observations, study liquids and weightlessness, and perform a considerable amount of photography. The day is May 24th, 1962. As Carpenter arrives at the launch complex and prepares to board his Aurora 7 capsule to fly the mission-designated Mercury Atlas 7, everything proceeds smoothly. A couple of modifications have been made to the Mercury capsule since the last flight. One of the primary components Carpenter will test are the new high-pressure maneuvering thrusters. Carpenter will also experiment on whether or not body movement has any effect on capsule orientation. Another test calls for him to inflate a balloon and trail it behind his capsule to examine spaceflight dynamics. In addition, he will study the haze layer around the planet noted on earlier flights. In all, the mission can indeed be marked down in NASA history as the first full work day in space. Downrange, the recovery personnel are mobilized and take their place. After Carpenter is sealed into the capsule and the tower is rolled back, it is determined that all systems are go.
Your attention, please.
We are holding at T-minus 11 minutes. Flight director, is this the weather hold? Affirmative. T-minus 18 seconds and counting. Engine start. 15.
Minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
I feel the liftoff. The clock has started. Roger. Loud and clear, Captain. Roger, Aurora 7, stand by for the time hack. Roger. Little bit of shaking. Pretty smooth. 3, 2, 1, mark. Roger, the backup clock has started. 4 minutes. Aurora 7 is go. Fuel and oxygen steady. Cabin holding 25. I am weightless and starting the fly-over turnaround. Ox stamp is good.
3rd, 1962, astronaut Wally Schirra takes his turn as the Mercury pilot. His Sigma 7 capsule will double the previous number of orbits and fly 6 times around the Earth in a 9-hour and 13-minute mission.
Yeah, I got the pins on my office wall. Altimeter's off the page. Stand by for 20 seconds. Okay. 2, 1, mark. Your backup started and running good. I'll give you a hack at 9:30. Oh, she's riding beautiful, dude. Mark, 30. Okay, fuel is okay.
Disaster nearly ends the mission early as the Atlas missile over-rotates during launch and is on the verge of aborting when the rocket auto-corrects.
Not at all too noisy. Easy to talk through.
Improved NASA filming equipment enables us to see rocket staging occur. The final Project Mercury mission was flown on May 15th and 16th, 1963. On this flight, Air Force Major Gordon Cooper is scheduled to complete 22 orbits in what NASA calls a full day in space. The length of the mission requires Project Mercury engineers to make sweeping changes to the capsule. Over 100 modifications take place in order to accommodate the quantities of oxygen, water, food, and fuel necessary to complete the mission. 12 experiments are planned, including the release of a lighted beacon for visual tracking exercises.
Seven, 6, 5, 4, 3, 2, 1,
Roger, have a lift off and the clock is operating.
Roger, clock.
Sigma 7, base 7 on the way. Standing by to start the backup clock.
Roger. 3, 2, 1, mark.
Roger, and the backup clock is running.
Roger, you look good here, Doyle.
Roger, feels good, buddy.
Great start.
30 seconds and fuel is go. Oxygen is go. Cabin pressure on the top. Sun is coming in the window now.
Roger, we're standing by for your beacon.
Roger.
Yet no mechanism, however wonderfully wrought by the hands of men, can substitute for man himself. A machine can be built to stand more heat, more cold, and perhaps take up less space. But engineers cannot fashion something as dexterous as the hand, as perceptive as the eye, nor can they make a brain with curiosity, imagination, and courage. Air Force Major L. Gordon Cooper confirmed all of this in the last and longest of the Mercury flights. Suiting up, the pre-dawn ride to Pad 14, the well-wishing, the squeeze into the capsule, and the long countdown wait has become a familiar ritual. But then the count reaches its final moments. Ignition. Liftoff. And a man is riding a flaming pillar of power. The only calm man present is Major Cooper, who remarks, "What an afterburner." But Major Cooper can scarcely be counted among the present any longer. He has left the Cape and the world below, and in 5 minutes will be going more than 17,000 miles per hour. He will be in orbit. More than 700 members of the press gaze at the diminishing speck in the sky. The news is trumpeted worldwide in a matter of seconds. Europe watches Major Cooper's launch live via Telstar. Major General Leighton I. Davis, commander of the Atlantic Missile Range, directs the 18,000 people of the Department of Defense who are committed to the support of Project Mercury. In the 19th orbit of Major Cooper's 22-orbit flight, the failure of an electrical relay eliminated his autopilot and attitude indicators. Without the astronaut, the mission would have ended here in failure. Ground controls could not have retrieved the spacecraft from orbit. Major Cooper fired the retro rockets and, using the window for attitude reference, manually controlled the spacecraft during re-entry. The landing was perfect, emphasizing the fact that the most important system in space is man himself. Major Cooper elected to wait in his spacecraft for retrieval by the nearby USS Kearsarge. The band on board strikes up the Air Force song as Major Cooper emerges wearily from Faith 7 and responds with a grin and a salute.
Go 1.2 G.
All the Mercury orbital missions required more powerful Atlas D boosters, and the Air Force and its contractors provided launch services to NASA on a reimbursable basis. The boosters, guidance systems, and launch facilities used for the Mercury Atlas missions were provided by the Air Force Space Systems Division. On-site management was carried out by the 6555th Aerospace Test Wing and its contractors, who had developed the initial Atlas intercontinental ballistic missile capability in the late 1950s. This veteran Air Force contractor team was now tasked to assemble, check out, and launch Atlases into their proper orbits for the Mercury missions. During the early 1960s, another version of the Atlas Agena B, was launched by the 6555th for NASA's Ranger and Mariner unmanned space programs. Within a few years, NASA was ready to work directly with the contractor and replace the Air Force as the government's principal contracting agency for Atlas launches.
GT-6, the first rendezvous and docking mission, was scheduled for October. Astronauts Wally Schirra and Tom Stafford were already in their spacecraft when the Agena target vehicle atop an Atlas booster blasted from the old Mercury Complex 14. After approximately 6 minutes of flight, telemetry signals were lost. The Agena never achieved orbit. GT-6 was scrubbed.